gas law. We're going to review just one more time. We're going to review Boyle's law because that's really the whole reason I'm covering gases is Boyle's law. Why? Because it's how you breathe. You think you're doing that. You think you're doing that. You think you can, you think that your lungs are a bigger deal than Boyle's law. You're wrong. You're wrong. You're not doing it. You're not sucking it in like a vacuum. That's not what's happening. What you're doing is you're inflating. You're making your diaphragm bigger. You're making it bigger. And what's it doing? It's changing the pressure. So your volume is increasing. Your pressure is decreasing. And now the pressure in here is lower than the pressure out here. And air is just going to come in. Oxygen is just going to go. And also at the same time, now you have all the CO2. It's you kind of need to get that out. So you're going to decrease that space. You're going to make it smaller. And when that happens, the gas is like, I'm out. Peace. I'm out. I'm out. I don't want to be in here. I want to be out. Because now I want to be where the pressure is lower. Do you see? This is really important because we're going to talk about respiration. And I need you to remember that we talked about this. Okay. That's Boyle's law. I'm not adding anything because I already added all that stuff in class. Blood pressure. This is really fun. We're going to talk about this more in physiology. I'm not going to spend a ton of time doing it now. You can look in your book. You probably already know this. You got diastolic pressure. You got systolic pressure. You got all kinds of good stuff going on. You're putting the cuff on. You're stopping the pressure, right? It's all about pressure. You think chemistry doesn't matter? You think gas law doesn't matter? You're wrong. It does because pressure is really important. So you're putting pressure on it. You're waiting. You're listening. You're listening for sounds, and then you're releasing the pressure, and you're releasing for the sounds to stop, and that's going to be your blood pressure. You can read all about that if you want to. And look, again, 200 millimeters of mercury. See? Now you know what that means. You can go back to that picture. Okay, so there are other people who made laws, not just Boyle. Charles, our buddy Charles, made a law. He made Charles's law, which is interesting. And Charles's law is actually a lot like the next law. So basically, Charles's law states that the volume of gas confined at a constant pressure is directly proportional to the Kelvin temperature. I don't know why it has to be Kelvin temperature, but Kelvin temperature. When the temperature of a sample of gas is increased, the volume increases. So when you heat up the gas, it starts to go a little bit crazier and the volume increases. Naturally, the volume just goes. So you've, again, seen this with balloons. It decreases, it increases. This is what's happening. Okay, so let's move on to the next law. Okay, so the next law is actually just putting these together. It's saying the pressure of a fixed amount of gas at a constant volume is directly proportional to the temperature. As temperature goes down, pressure goes down. So this one was saying as temperature goes up, volume goes up. This is saying the same thing about pressure and temperature. So both of these are temperature, basically. So we have all these people saying all these things about gases, and so we have a combined gas law. So we took all the people and made one equation. So instead of just talking about pressure and just talking about volume and just talking about temperature, we made one equation so that you didn't have to remember a bunch of equations. You just had to remember one equation. And that is the combined gas law. That is combined gas law, people. Boyd, Charles, and Gay-Lussac all have laws that can be combined to form combined gas law. Combined. I see it. Gas law. I'll fix it in a second. Okay, let's not have two C's there. Okay, combined gas law. There's problems. We'll talk about those in class. We'll talk about problems. I don't know how many of those we'll do on the test. We'll do some in the homework, but I don't know that I'm going to ask you a lot of it on the test because mostly I'm really just concerned about Boyle's law and your lung capacity and that you remember that when we get to that part of physiology. Okay, so now we have Avogadro's law. Do you just feel like he's got all kinds of stuff with equations and math and he never ends? Okay. So he says the volume of gas is directly proportional to the number of moles, because you know he's going to have something to say about moles and all the molecules in the gas. He's not going to be okay with just the equation. He's like, no, we got to add my number there. We got to talk about how many molecules are flying around in a mole of gas. So he adds that, and that uses standard temperature. So then we get ideal gas law. So let me tell you a little something about ideal gases. They don't exist. It just does not exist. There is no ideal gas. It doesn't exist. It's a myth. but we have to talk about it in perfect conditions as if it existed. So pressure, volume, and temperature can be conformed, can make another equation. So pressure and volume equal basically this constant and temperature. So that's what's happening. Or you can rearrange the equation to look like this, and you can rearrange it like several different ways, as you'll see if you do any of the problems. The relationship among these variables can be combined in a single expression called ideal gas law. And that is where you get ideal gas law. I give you variables, you play with them, you move them around, and you get ideal gas law. The constant R, so this constant or this constant, depending on which one of the equations you use, is a gas constant. Its value depends on the units chosen for pressure. So here's an example. The ideal gas law is used for determining parameters of a sample of gas whose volume, pressure, or temperature may be changing, but when the number of moles of gas is constant. So we know the moles. We have a mole of gas, 6.02 times 10 to the 23rd particles of gas. And we can mess with it. We can change the temperature or the pressure or the volume, and we can do things to it, and we can play with it. Because that's what you do in your spare time. I know it is. So that is gas law. You can do fun stuff with gas law. We will do some problems in class. You can do your homework, which I know you want to do. And you can also look more on blood pressure and lungs, which we will talk about in much more detail when we get to that chapter in chemistry, when we get to that chapter in physiology, and when you inevitably get into nursing school, or when you move on in in physiology, if you would like to. So for now, I just really want you to understand this issue with gases about how pressure will change that, and temperature. So the temperature in your body, you have a fever. How is that going to affect how you're breathing in and out? The volume of your cavity, if you can't breathe in and out, we're going to talk about smokers and how they can't breathe in and out, and how is that going to affect what's going on with the pressure, because you're not doing it. It's not a physical act of moving in and out. It's all about the gradients. So what happens if I puncture your lung? What happens if I stab you with a pin in the lung? What's going to happen? It's going to change that temperature. It's going to change that pressure gradient. All of a sudden, the pressure outside is the pressure inside, and oxygen isn't going in. Bad things are going to happen. Don't puncture your lung. That would be bad. Okay. But next is liquids.